so we have the weak Elmer's glue of intermolecular forces, the London dispersion force for nonpolar molecules that don't have a substantial permanent region of charge. They can maybe just create these temporary regions of charge when the electrons move in a way that puts them not equally dispersed around their central atoms. We've got the little stronger intermolecular force, maybe like the hot glue of intermolecular attractions, the dipole force, which is for permanently polar molecules that always have this region of partial positive and partial negative charge. And so the particles will line up so that those regions attract each other. There's attraction between the molecules. And now here's the third, the hydrogen bond. This one's kind of special. In reality, it's a special type of dipole force. The concept behind this is exactly the same, where you've got molecules that are permanently polar, like water. And think about drawing a water molecule. Water, we've drawn this dot structure probably a bazillion times. I got my oxygen, I got my two hydrogen, boop, and here's the other one, single bond, perfect. So I think about electronegativity, and I know that oxygen is right next to fluorine. And fluorine is the highest electronegativity, so everybody else close to fluorine is also really high. That they've almost got full outer shells, and they really want to gain a few more electrons to fill those outer shells. Well, yeah, oxygen's going to have a higher electronegativity than hydrogen. And so these are polar bonds, meaning that within the bonds, the electrons are not shared equally. They're going to pull closer to oxygen. Well, now I've got these two polar bonds, but they're not equally arranged around the central oxygen. This is one of those bent molecules. There's nothing else to balance the pull. And so instead of these little pulls canceling, there's just this net pull for the electrons to be up closer to the oxygen. And that's going to make the oxygen region of the water molecule partially negative. Partially negative. The electrons are being pulled up toward the oxygen, which then also means that the hydrogen region is partially positive. The electrons are lacking in the region of the hydrogens. They're being pulled toward the oxygen. Now again, this is polar for life. This is a polar molecule for life. The electronegativity of oxygen will always be higher than hydrogen. The molecule will always be bent. We're always going to have this partial negative oxygen and partial positive hydrogen region of the molecule. And so then I look at this picture and it kind of makes sense. It looks just like the dipole force, right? Where every time I have, in the middle, there's that red oxygen that's got the partially negative sign on it. Well, if you put a whole bunch of water molecules together, they purposely align so that opposites attract. That the partial negative oxygen is always attracted to the partial positive hydrogen of another molecule. And so it's over here. It's down here. Here's the oxygen. It's a little negative. It'll line up so that it's attracted to the partial positive hydrogen of a neighboring molecule. That attractive force in between the molecules is called a hydrogen bond. It's between the molecules, not within the molecule. This thing right here, that is called a polar covalent bond. That is very strong. Ionic bonds, covalent bonds, that's a strong attraction. Now, these intermolecular attractions are weaker than bonds, but they do increase in strength. And so this hydrogen bond is a little bit stronger than a typical dipole force. The concept is exactly the same. Exact same concept, that you've got partial positive and partial negative regions of polar molecules, and they align themselves so that opposites attract. And we get these attractive forces then in between the molecules. It's just that this whole hydrogen bond thing is a little bit stronger. So a little bit stronger than gosh, what did I use? Hot glue, I think. I used as an analogy. If London forces are like Elmer's school glue and the dipole force is kind of like hot glue, maybe this is kind of like super glue. This is a really strong intermolecular force, but it's not as strong as a bond. But here's maybe why it's a little bit stronger. Number one, you've got baby hydrogen. I mean, obviously, if they call it a hydrogen bond, there's going to be hydrogen. Yep. Hydrogen bonds always involve hydrogen. And the problem with hydrogen is that he's such a small atom and he only has one proton and one electron. And so it's really vulnerable. If you bond that little baby hydrogen to another atom that has a pretty high electronegativity, I mean, if they're going to share it all, they're definitely not sharing the electrons equally. The bonds are really polar because there's only one little proton in the nucleus of hydrogen that's trying to hold on to his one little electron. But the problem here is that the little hydrogen atom is bonded to something very electronegative. Now here they're saying commonly fluorine, chlorine, oxygen, or nitrogen. Typically, we think of it as FON. And I guess you could argue chlorine, but typically we say hydrogen bonding is FON. FON. You got to have hydrogen bonded to either fluorine, oxygen, or nitrogen. What's so special about FO and N? They have the highest electronegativities on the entire periodic table. The bond between hydrogen and fluorine is about as polar as you can get while still sharing the electron. I mean, that poor little electron in hydrogen is almost completely ripped off. It's almost ionic. It's just barely hanging there by a thread. And so this is the exact same concept as the dipole force. It's kind of just like a little bit more extreme version of a dipole force. It's just a little bit stronger because this partial positive and partial negative is just a little bit stronger because baby hydrogen barely has a hold on his one electron, and he's bonded to the three biggest electron bullies of the whole periodic table. The bond is really, really polar. And so these regions of partial positive and partial negative are just a little bit more extreme. They're a little bit more intense than a typical dipole force. But again, hydrogen bond, obviously you have to have hydrogen, but it has to be bonded to F, O, or N. So here they're giving us an example of like CH4, but if you were to sketch CH4, which we did previously, there he is, CH4 is a nonpolar molecule. And so there really is then no substantial region of charge. And so you can't just say, well, anytime there's a molecule with hydrogen, it's going to have these hydrogen bonds. Sometimes you kind of have to sketch the structure first. If it's a nonpolar molecule, then you're only talking about those weak London dispersion forces. Polar molecules will either have dipole forces or hydrogen bonds. And that's the trick with the hydrogen bond. It has to be hydrogen bonded to F, O, or N. And they do kind of mention here too, I wish it was called, I don't know, like a hydrogen force or something. A hydrogen bond is not a bond. It's a force. Now, it's a little bit stronger intermolecular force, but it's still weaker than these bonds. It's not an ionic or covalent bond. It's a force between the molecules. So I wish it was called like the hydrogen force, not the hydrogen bond. A bond is ionic or covalent. A bond is sharing or transferring electrons. Here we're talking about this attraction in between the molecules, the molecular glue. So question 22, we're going to look at the bonding between hydrogen and fluorine. Hydrogen fluoride molecules. Explain whether hydrogen bonding is present. Well, I mean, the easiest way to do this is to say, do I have hydrogen bonded to FON? Well, yeah. When a hydrogen is bonded to fluorine, oxygen, or nitrogen, that's when you're going to create hydrogen bonds. Hydrogen bonds. Okay, but here's the deal. So let's say I like draw a Lewis dot structure for HF. Super easy. HF. 1 valence electron hydrogen, 7 valence electrons around the fluorine. Connect the dots, good to go. Now let's say I keep it in the halogen group, but we go like hydrogen and bromine. So let's do hydrogen and bromine with his 7 valence electrons. So the structures are really similar, right? Okay, so here's the deal. They're both polar bonds. The fluorine and the bromine have higher electronegativities than hydrogen. But the problem is fluorine has a really high electronegativity. So in both cases, the electrons will be pulled toward the halogen. They'll be pulled toward the fluorine or the bromine. But here it's like big time difference in electronegativities. That poor little electron on hydrogen, it's almost completely removed. This bond is as close to ionic as you can get, while still sharing the electron. So it just makes this region partially negative, but like extremely partial negative. And this region is extremely partial positive. Where it's the same concept with hydrogen and bromine, it's just that bromine's electronegativity isn't quite as intense as fluorine, so the electrons still pull toward bromine, and it's still a polar molecule where the bromine region is partially negative and the hydrogen region becomes partially positive. It's just not quite as extreme. And so they're both polar molecules, but because of the extreme partial positive and partial negative, we would say that HF molecules are connected by hydrogen bonds, whereas the hydrogen bromine molecules would just be connected by dipole forces. It's all about the extreme difference in electronegativities. Poor little hydrogen bonded to FON, that poor hydrogen, his electron is really strongly pulled over to the FON. They're the most electronegative elements on the entire periodic table.